So Newton's first law says if you have a puck in motion and it's moving at a constant velocity, as we have right here, then that puck is going to remain at that constant velocity. There's no forces acting upon it. It's not accelerating. Now if we consider in part B here a puck that is accelerating, it's going to have a small velocity. The force is still being applied to it, and the velocity is going to get longer and longer and longer and longer. So the velocity is changing, therefore this puck is accelerating, and it has your hand, the force, that is pushing on it with a constant force across this. Now the key thing to note here is that the force and the acceleration are in the same direction. In the case where the force is going to be slowing a puck down, where we have the puck moving at some velocity from the left to the right, but the force is acting from the right to the left, therefore the acceleration is also going to be acting from the right to the left. So force and acceleration are always in the same direction. The velocity vector is going to get smaller and smaller and smaller and smaller. So again, force and acceleration are always in the same direction regardless of velocity. Now we've already talked about circular motion a little bit. If we have an object that is going around in a circle, it has a velocity that is perpendicular, or that is tangential to the motion of that circle. So at any given point we can write our velocity like that. And we've said, okay, this has to be accelerating towards the center of the rope. We're talking about maybe uniform circular motion, not the non-uniform case. It has an acceleration that is directly towards the center of the circle. Newton's second law that says force and acceleration have to be in the same direction says that the force is provided by the rope, and that would actually be some tension force in the rope that's providing that. So Newton's second law, written out in all of its glory, says that the acceleration object is directly proportional to the net force acting on it and inversely proportional to the mass of an object. And it's kind of written like this, where this again is the sum symbol. The sum of forces is equal to the mass times the acceleration. And again, this is occasionally written as the net force. It's just kind of shorthand. So let's think about this for a little bit. If you push an object with a given amount of force, then it's going to accelerate. Now, if you push that object with twice the amount of force, then it's going to accelerate twice as fast. If you push it with 3 times, it's going to accelerate with 3 times the acceleration. If you think about the inversely proportional aspect of it, if you push an object with some unit of force and it has some mass, then you know that it's going to accelerate. But now imagine pushing an object that is twice the mass. What that means is it's going to accelerate twice as slow. So would you rather help your friend push their car to the side of the road when it has a flat tire or something, or when it has a engine breakdown or something like that? Or would you rather try to push a locomotive that is much more massive? Right? You might be able to accelerate the locomotive, but it's not going to be pushed forward nearly as quickly, given that you and your buddy have the same amount of force. Now, the SI unit of force is going to be the Newton, named after the man that came up with these 3 laws, and 1 Newton is going to be 1 kilogram meter per second squared. And looking at our equation, we can kind of see where that comes from. Kilogram is the unit of mass, and the unit of acceleration is meters per second squared. So a Newton is simply a kilogram meters per second squared. This also says is if you observe or you measure an object's acceleration and you also measure an object's mass, then you can calculate how much force is required for that acceleration to occur, for the velocity to change. So let's apply Newton's second law, and we're going to do something where we draw what we call free body diagrams, which is essentially all of the forces acting on a body. And here we have a fella pushing a block, and this block has a mass of 40 kilograms. And when we draw all the forces on this box, a free body diagram if you will, we draw the fellow's 20 newtons on the block, and you say, okay, I'm done. But that's not quite true. We have two more forces acting on this box. We have the object's weight, which is due to gravity, and then we have the normal force, or the support force, from the ground. Now that we've drawn all the forces on this box, let's take a look at the x and the y directions separately. So here we have the x direction, here we have the y direction. Let's say in the y direction, let's sum up all of our forces, and that's going to be equal to the mass times the acceleration in the y direction, and that's going to be the normal force in the positive y direction and the weight in the negative x direction. Now, it's very rare that I've actually pushed a box from the left to the right and it has accelerated up or down. So the acceleration in the y direction is actually equal to 0, and what this says is the normal force is equal to the weight. Now, this is true when we're looking at objects that don't have a slope to them. This may not necessarily be true when we look at ramps. And in the x direction, the sum of forces in the x direction is going to be equal to the mass times the acceleration in the x direction, and that's going to be equal to 20 newtons. So I can go ahead and I can solve for my acceleration. It's going to be my 20 newtons divided by the 40 kilograms, or 0.5 meters per second squared. Let's take another example, and in this case we're going to marry some of the forces that we're talking about to some of the concepts of motion that we talked about in chapters 2 and 3. Let's draw first all the forces that are acting on this bottle of milk that is sliding, and we know that it's going to have some initial velocity and some final velocity, and it's going to travel from some initial position, I'm going to call that 0, to some final position that's equal to 1 meter. And this jug of milk also has some mass. Now we see that it has some initial velocity in the positive direction, let's say, and then it finishes at 0. The velocity has changed, therefore there has been some acceleration of this milk bottle. There must be a force. If there is an acceleration, there must be a force behind that. And in this case, we can see that the force must be in the backwards direction. And if we think about the velocity of our milk, the frictional force is always going to be in the opposite direction as the velocity. And just like in the last case, we still have an object's weight, and we still have the normal force. And just like in the last case, the sum of the forces in the y direction are equal to 0, so we can just simply say that the normal force is equal to the weight once again. Now, in the x direction, we're also going to say the sum of the forces are equal to the mass times the acceleration. we can use kinematics to first solve for the acceleration by saying that the velocity in the x squared is equal to v naught x squared plus 2 times the acceleration, and here I have x minus x naught. I know that the final velocity is equal to 0. I know that my initial position is equal to 0, so I can say that the acceleration must be equal to negative v naught squared divided by 2. I go ahead and I plug all that stuff in, and I come up with negative 3.92 meters per second squared. The negative meaning that it's in the negative direction, slowing this object down, acting in the opposite direction as the velocity. So now I can say that the sum of forces is equal to mass times acceleration is equal to the force of friction. So I can write the force of friction is equal to 0.45 kilograms multiplied by negative 3.92 meters per second squared, or negative 1.76 newtons. These are the frictional force that I have in this case. Now I've already talked about this a little bit. We're using the SI system in this class, and other systems that we might see would be the CGS system or the Ridge system, CGS being centimeters, grams, seconds. Some engineers still use this system, but really everyone is moving away from it. The units of mass are in grams, acceleration in grams per centimeter, and the unit of force is actually a dyne. I've never seen this system being used except for in like really old textbooks. We'll stick with the metric system using forces as newtons. The one that we're kind of more familiar with is going to be the pound, and if you step on a scale it's going to read your weight in pounds. Something we're not as familiar with in the British system is the unit for mass. That is actually a slug, and we tend to get confused, especially using British system for everything that we do, distinguishing between an object's weight, which is a force, and the object's mass. So I'm going to talk about this more on the next slide. Now, there is a huge difference between mass and weight, and this is often confusing. The weight of an object is the gravitational force that the Earth exerts on it. So the weight is a force that is acting on something. The mass is a property of the object. It's how much a body resists acceleration, or how much inertia a body has. The force is simply the force that the Earth exerts on it, and we can write that knowing the mass, so this is the weight of an object, as well as knowing the gravitational attraction from, in this case, Earth, which would be the number that we've used already, 9.81 meters per second squared. Now, in reality, the value of g depends on altitude. We'll go into that in a couple of chapters when we talk about Newton's law of gravitation. You know, for right now, say gravity is equal to 9.81 meters per second squared. Now, something to keep in mind is if you have an object with some mass, let's say it's 10 kilograms, we can go ahead and we can calculate the object's weight. In this case it would be 10 kilograms multiplied by 9.81 meters per second squared, so that would be 98.1 newtons. Now if I take this object to, say, the moon, where the gravitational attraction is 1.6 meters per second squared, the mass will not change. The mass is an inherent property of the object about considering how much it resists the acceleration, how much inertia it has. The weight on the moon is going to be the same thing. It's going to be 10 kilograms, only now multiplied by the gravitational attraction it feels from the moon, 1.6 meters per second squared, and we're going to come up with 16 newtons. A lot of the confusion that we get from this is because we're used to thinking in the British system, where pound, we think of that, we step on a scale, we see pounds, and we think that's related to how massive we are, but really it's related to how much force the Earth exerts on us. If we took that same scale to the moon, it would read something very different. Just to kind of hammer home this point, if we consider a euro in free fall and rewrite the sum of the forces on that, that's going to be equal to the object's weight, where we know the object's weight is equal to mass times gravity. So we can say that the sum of forces on this guy is equal to its mass times the acceleration is equal to mass times gravity. The masses go away, and at the end of the day we see that the euro is going to fall at 9.81 meters per second squared. Now, Newton's third law is something you may have heard in pop culture or something like that, where it says, for every action there's an equal and opposite reaction. And what Newton's third law says, if you exert a force on a body, that body is always going to exert a force back upon you. That would be a reaction force, and this would be a force of action. So the figure below shows what we would call in Newton's third law an action-reaction pair, a foot kicking a ball. And the key thing about Newton's third law is that the action force and the reaction force have the same magnitude but opposite directions, and these forces act on different bodies. So here we have a foot kicking a ball, and that foot is going to exert a force on the ball. Newton's third law says that the ball is going to push back on the foot with an equal force, just in the totally opposite direction. So the forces are acting on different bodies, the ball and the foot. And if you think about it, the force of the foot on the ball is going to cause the ball to accelerate, and the force of the ball on the foot says, hey, I can feel the force of the ball up against my toes. So different objects, foot and ball, magnitudes of the forces are the same, just in opposite directions. So let's take a look at applying Newton's third law to some objects at rest. Let's consider an apple sitting on a table. Now the apple is going to have a force downward that's due to its weight. This is the force of the earth on the apple, and it's going to be supported by the force of the table on the apple, because obviously the apple is not going to plummet down to the earth when it has a table underneath of it. However, while these forces are equal in magnitude and opposite in direction, these are actually not an action-reaction pair. So let's take a look over here at B. If the earth exerts a force on the apple, this is going to be downward, and what Newton's third law says is that there needs to be a force of the apple on the earth that's going to be equal of magnitude and opposite of direction, hence the negative sign right there. Now the table is going to have a force upward on the apple, force of the table on the apple, and the apple is going to put a force downward on the table. So here we have the force of the table on the apple and the apple on the table. Here we have the force of the earth on the apple and the apple on the earth. So when we talk about action-reaction pairs, it needs to be earth on apple, apple on earth, table on apple, apple on table. So looking over here where we had the force of the table on the apple and the earth on the apple, right away you can kind of see that this is not an action-reaction pair because these equal and opposite forces are not acting on the same objects. And we can eliminate one of the forces acting on the apple. If we remove the table, an action-reaction pair still needs to exist. In this case, it's going to be the force of the earth on the apple and the force of the apple on the earth, and the apple will accelerate down towards the earth. Now, you might be thinking to yourself, how the heck can anything actually accelerate if an object pulls or pushes back on you just as hard as you pull on it? I mean, is this a paradox? And it turns out we need to very closely consider our action-reaction pairs. In the case of a mason pulling on a block with a rope, what we really need to look at is the floor, the friction force on the floor. Now we know that the force of the mason on the rope and the force of the rope on the mason are action-reaction pairs, and essentially the mason is not going to move as long as this force of the rope on the mass is equal to the friction force on the floor. I mean, if you think about it, if there was no friction force, then the mason could not exert a force on the rope from the mason. So essentially what we're saying is that the mason cannot pull on the rope any larger than what his friction force will allow. Now the same thing is true for the block and the rope. The block will not move as long as the friction force of the floor on the block are the same. Now the friction force for the floor on the block is going to be different than the friction force of the floor on the mason, and that's how this system can accelerate. What this is also saying is, if you think about when you're playing tug of war with your buddies, it's not really about who can pull harder on the rope, because that's an action-reaction pair. It's who has more friction force on their side.